Hello, this is Robert Bolaños. Welcome to Forward Converter Part 9 Multiple Output Converter. Okay, so what this is going to be a design example. Okay, and I'm going to be using these specifications to design a very simple forward converter, but it's going to be with multiple outputs, which is a little bit different what I've done. Excuse me. So this one we're going to go with 3, and one is going to be at 3.3 at 3 amps, the other at 12, 3 amps, 18 at 3 amps, and so forth. So when you're designing a transformer, you have to select the proper AP. Okay, this is the area product, and I believe this is in could be in centimeter to the 4th. Okay, so we're going to use this, find out the AP of the core that will satisfy the requirement, and they also have an equation that if you have, I believe, the AE, the switching frequency, and let's see what else. Oh, and the power. Then, oh, actually not the power, but I believe, let me see. It's another another parameter. I can't remember right now, but we'll see. But you can calculate the power. Okay, so we'll see that later. Then we'll do a turns ratio, and then we'll check that the B field does not exceed the maximum or the saturation flux level of the transformer. Okay, so we're going to do that example. So the first thing that you want to do is you want to calculate the output power, which is the first step. In this case, you multiply the voltage, the output voltage, times your output current. Excuse me. And that will give you your power levels, and you have those shown here, so you end up with a total power. Okay, so now this is output power. Okay, so now you have to translate that. Okay, you want to translate it to the input. Okay, so let me see if I can. So you have this box, it's your power supply, and let's just to simplify it, at the output you're going to be consuming 99.9 watts, but at the input you use this equation, which is Pn divided by the efficiency. In this case, I calculated 124.8 watts. Okay, so the difference between this and this is consumed by the power supply. Okay, so it's roughly 24 watts is being dissipated as heat in the converter. Okay, so again, this is, you get the output power divided by the efficiency, and a forward converter you can assume an efficiency of 80%, so you basically is a 0.8. Okay, and that's a conservative number. You can make it more efficient, but start off with 80%. Okay, so you end up with this. So this is the input power. Okay, so now once we have that, what the power is, and the reason we need the power is because of this equation. And put it in red because it's an important equation. Okay. This equation allows you to calculate the AP that you would need to be able to, for your transformer or the core that you select, be able to dissipate, or not dissipate, but at least be able to handle your output power. Okay, so that's an input that goes in there. Okay, and then this K is a factor, and I believe this equation comes from an old TI application note. Okay, and the K, or that factor, is 0.014. Okay, which is right there. Excuse me. Okay, and then this B factor, I'm choosing to set it to 0.11 Tesla. Now this BS is the flux level that you're going to be using in the core, and I'm setting it to 0.11 Tesla, and this is so I can get some agreement with the Pressman book. Pressman has a chart with these numbers already calculated, so I'm using that just to be consistent with this. So I'll go ahead and use that. And then the frequency, that's the frequency. See, okay. In this case, I'm setting it to 100K kilohertz. Okay. So when you insert the numbers, okay, your K, your flux, your frequency, and your power, I end up with this this number. Okay, that number then you can use on your data sheet. Okay, in this case I have these are in millimeter to the 4th power. Okay, So to convert this, you divide by 10,000, so you can convert that to AP. Okay, so that converts to that. So you have to select an AP that is higher. Select that is greater than this AP. Calculate it. Okay, and this is from the core. So in this case, you can come up here and I had calculated here on this one, sorry, that I needed 7,555. And if you notice, this one is in red because it's lower than 7,555, and so are these. But if you notice, this is green. Okay, so that means, and this is 10,000, so this is green. So this, the program is telling me that I can use a RM12 to design my power supply. Okay, so that's how we use that. Now there's a second method, and if you notice, again, you can use this equation, and if you use this equation, you can also make a chart if you solve for PO. In other words, use this equation, solve for PO, which is the power out, and you end up with this equation, which is very important or very useful. Okay, because then with this equation, if you know the core, the AP of the core, you can plug it in, and then you can define these. Then you can calculate how much power that core is capable. Okay, so in this case, since I'm using the RM12, it has a AP of 1.0915 centimeter to the fourth. When I enter that into this equation, it tells me that it can handle up to 164 watts. Well, that is greater than this. Okay, so it satisfies basically. So in this case, you have two methods to select the core. Remember, we have a power. Let me change the color here, of 124 watts. Okay, and if you use the P core, we calculated that the RM12 get 164, which is higher than the 124. So that's correct. That's a chord that we can use. Likewise, you can also use the AP method. So if you calculate the AP and it's greater than what you calculated, then you can use that core. In this case, if you notice, let me go back. On this column, I have power calculated, it's green, and I have the AP calculated, it's green. So that means that I can use the RM12. Okay. Okay. So now that we got this out of the way, or at least selected, we can use a spreadsheet, which is what I'm using. I'm going to show how I use this spreadsheet, but I'm also showing some of the equations, or basically what the spreadsheet is doing. Now this is typically the equation that we use for design. And this is based, or it's using the fact that you want to stay away from your BSAT. And usually BSAT is around 0.3 Teslas. BSAT is the saturating point of your magnetics. In other words, if you have a magnetic and this is the flux, and then this is your current, as you increase the current, the flux goes up, and then at a certain point the flux no longer increases but just stays the same level. So this little knee is BSAT. That's the limit, and you want to stay away from that. Okay, and typical values on most of the ferrite, or a rule of thumb, is 0.3 Teslas. Okay, so you want to keep below that. So BSAT should be less than 0.3 Teslas. Okay, so got that. So now you have this equation, and let me go ahead and erase a little bit of this, that way it doesn't get so confusing. Okay. I'm going to keep this a little bit neater. Okay, so here's the equation. This is voltage, E. You can put voltage there, or a V. And this is T on. Okay. Another way of representing T on is duty divided by the switching frequency, which is what I did here. Okay, and this is AE. This is the effective area of the core, in this case right there. Okay, now that is in centimeters squared. Okay, but we have to convert it into meter squared. So when you convert, this is the conversion, okay, which is AE, and then B operate. So this is the number. In other words, you want B operate. I'll write it down here. To be less than B sat. Okay, in this case B sat is 0.3 T. Okay, so now if you notice here, I use a B sat of 0.063 Teslas, and then this is the frequency. Okay, and then this is the duty cycle, 42, and here's your input voltage. So when I plug that in, it tells me that the primary turns is going to be around 10 turns. Okay, so let me go to the back the spreadsheet. So remember, what I'm doing, I have this equation in the spreadsheet, and all I'm doing is I am varying this, your B operate, and as I move this operate or change it, I change the turns ratio, or this turn of the primary. So let me show you how that is done, or how it looks. So I scroll up here, okay, and let me go over this. This is a spreadsheet in Excel, and here's the operating circuit parameters. Here's the K factor. This is from the design equation, the frequency. Here's my B operate, input voltage, duty cycle, efficiency, and I have temperature. So basically what I have in yellow are things that I can input, okay, and anything in blue are answers or calculation results. Okay, so where you see a yellow, that means I can input. Okay, so the first thing I want to do is here under the transformer designer, under the primary, it says VN, and then right here this is the voltage output. So for the first winding I put in 3.3, 3 amps, 12 volts, 3 amps, 18 volts, 3 amps. So then it calculates the power, and then that power is added here, okay, and then it translates it to a input power, which is right there. Okay, so then once I have that, okay, once I have this set up, then I can come here to my RM. Typically this would be filled with different numbers. Let's say it would be a pot core, okay, or a different magnetic. But let's say I like this magnetic, and I say, oh, this is the one that I want. Then I copy this, and then I paste it here, right there. Okay. So yeah, I'll paste it there, and then if you look in here, B operate, I can move this operate, and let's say I start with 0.16, which is what Pressman recommends to start your design with 0.06. And if you notice right here, I have a turns for the primary, this is the primary, of 3.9. okay, now from that, then it calculates the turns ratios for the next 3 windings. But the point is that for this particular, if I make this a 4, then this is going to be let's see what happens. Show excuse me. So this I round it up to 4, and then I can override it and say change this excuse me. I can change this to 4, and if you notice, then the turns ratio is 1.56. Now you can't do half turns. Okay, it has to be uh, integrals. Excuse me. So I cannot use this as a term. So I want to make sure that I end up with a whole number. Okay, so then I can go ahead and play with this. Can make it even smaller. This is increasing. I'll come back to here, and mind you, we can't do a 6.3 turns. It has to be either 6, 7, 8. It has to be a non-integer number. Okay, again, if you notice, you have an integer here, and what you want to do is you want to get close to where this fraction is small enough. Okay, so anyway, so if we go 0.063, I come out with 10 turns, and if you notice, it has a real small fraction, so this is insignificant. So I can go ahead and just say 10 turns, and if you notice, this is only 0.1 away from 4, so I can set that to 4. This one is 13.6. I can set it to 14, round it up, and then this one says 20, and I round it up to 21. And let me show you why I'm rounding it to 21, because if I set it to 20, if you notice right here, I will get 17.7 volts, and this supply I need 18. Okay, so it's going to be a little lower. So if I go to 21, I get 18.5. Likewise, if I had lowered this to 13, I would not get 12 volts. Instead, I would get 11.4. So I can go ahead and set this to 12. Okay, and again, this one, if I go lower than 3 or go to 3, I won't get 3.3, I'll get 3.4. But if I go to 4, most supplies or can handle a little bit extra. So in here, I have 89 milliamps or millivolts above that. So I can live with these voltages. This looks good. So these are the turns ratios, or the turns. So I'm going to have a 4 to 10, which is turns ratio, and this number is what I will be using in Spice to simulate, and I'm going to try and verify whether these are good ratios. Okay, so 12 divided by 10, 1.2, 21 divided by 10, 2.1. Okay, so let's go ahead, take a look at Spice. Here I have the turns ratios already. This is NR1, and here this is the primary, this is the secondary, this is the 3.3, this is the 12. You can see if I can zoom in. This is the 12, this is the 15. Okay, and if you notice right here when I defined it, excuse me, this is LP, in other words the inductance that's in the primary, times NR1 times NR1. Okay, so basically it's NR1 squared. Likewise, this is NR2, and NR3. Here I have them designed. Okay, so let's do that, and let's see if we can take a look, see whether how close I come. Okay, if you go here, voltage there is 3.15. This one is 3.3, so it's a little lower. Okay, go to the next one. 12. This is 12.16. This one says oh, it's going to be oh, this should be 14. Okay, 12.3. Okay, and then the next one, 18.48, 18.59. So indeed it's very close. So it tells me that this design should be a workable solution. Okay, so let's see, let's go back here. Okay, so now in this case I use the spreadsheet to calculate this. Okay, and basically to calculate these and the turns ratio, these are the equations. Okay, and if you notice, you plug in, if you have a 10 turns, plug it in, it tells you what the turns ratio. So basically these equations is what is being used to calculate these numbers, or this turns ratio. Okay, so you can do it manually, or you can do the spreadsheet and do it that way. Okay, so basically, let me see if I make sure that these numbers where it says suggested turns are calculated using this equation. Okay, so now the next step is we have to calculate the RMS of all the windings. Okay, so the first winding is the primary, and in this case we have to use the input power. From the input power we calculate the average, and from the average we calculate the peak. So once we have that, we can plug it in and we end up with the RMS of 8.67. So that equation then is used right here. Okay, so it calculates it right there, pretty close. Okay, then for the secondary, we know what the output current is. It's going to be 3, and it's going to be 3 amps in all 3 supplies. So we use that equation to calculate the RMS. If you notice, let's see, what does it say? 1.94. 1.94. Okay, and all 3. Okay, so now we have that. So now we get to the point of selecting the wire size. Okay, and we have to select the wire size that can carry the current. So there's several ways you can do it. You can use a magnet wire capacity chart. Basically you can, it's a chart that actually it looks like this, a wire table. Let me see if I can. Okay, so here's a wire table, and it's got the diameters, inches, and then it tells you the current capability of that wire. So you can use this. So for example, in the designer for the primary, I need a wire that can carry 8.75. So I would come here, 8.7. So I can use a 17. Okay, 17. All right. Now this case, in this chart, I have equations that can calculate the current based on the wire size, or actually based on the current. So this is telling me, it says suggested AWG. It's suggesting to me, and let me go ahead and resize this to 1. I'll explain what this is. Okay, this is 8 amps. So to carry 8 amps, the program or the spreadsheet, it's telling me that if I use 1 wire, then I should be able to use a 17 American wire gauge to satisfy this 9.6. So what happens if I use something much smaller? Let's say, but let's go to a 20. I'm sorry. Let's go to a 20. And if you notice, the 20 can only carry 5.9. This turns red, so I can't use the 20. Just like the chart says here, I'm sorry, just like it's a 20, see 5.8, can't carry that. So this is kind of neat, because then I can go ahead and start playing with this. A 19, no. 18 perhaps, no. 17, yes. Okay, so this is the wire size. There, 17, 18, yeah. Oh, there. Okay, I didn't have this protected. That's the problem with not protecting it. Anyway, you can go with 17 here. This disappears and looks good. Okay. So then these are 1.9, 1.9, 1.9, and this is telling you if you use 1 wire, 1 strand of, in this case, 20, 29, and 29. Okay. So in this case, you notice this is red, so this wire is too small. So how do I fix that? Okay, so this one, a 29 gauge, can only handle 1.2. Okay, so this says that I can use the 26. Okay, that goes away. Okay, 29 can only handle 1.2, but it's telling me that I can put a 26. That goes away. So now I can basically, if I set these and use the recommended wire gauge, I have a design. Now the total power loss calculates the core losses and calculates the wire losses. So as you punches these numbers, it calculates the length, and then it calculates the resistance of the wire. Here's the resistance of the wire. It also calculates the power. That power is here. Okay, so this is our first pass design. Oh, can't do that. Okay, so we're going to use here, this is the 5.509 watts, or yes, watts. That's the power loss. Okay, so we should be able to optimize that, and I'll show you how. Okay, I got that. So I'm recording this. We want to make this lower. Okay, so how do we optimize? Okay, and one thing that I want to show here, it says percent okay. So here, this is percent of layer filled. So for the primary, the first layer is 85% filled, 24, 44, 67. Okay, what does that mean? With the layers per fill. Okay, let's see if I can explain that. So when you're doing a transformer, your first typical layer let's pretend that this is the first layer. That's going to be the primary. Okay, and then you end up winding a second layer, and of course you put a insulator, and let's say it's Teflon tape. And then you can do another layer and so forth. Okay, so when I'm talking about percent filled, is due to the wire size. Okay, so the primary has 10 turns. That means there's going to be, when you wrap it, that's 1 turn, 2 turns, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, it's saying that it's 85% filled, meaning that this, from here, let's say this is 100%, 0%, this is 100%, that it's filled to 85% of the layer. And typically you do not want partial fills. See, because you have this space that is not used. Okay, so what you want to do is you want to expand this if you can. Okay, sometimes you can, sometimes you cannot. But let's say you have 3 turns, as in, or actually 4 turns. So you would have 1, 2, 3, 4, and then you have this much space not used. Okay, so typically you want all of it used. Okay, and we'll see what how to do that. Okay, so I'm gonna go ahead and leave that at 85. Okay, and I may come back to it, but I'm gonna start with this one first. If you notice, this is 67. So to fill it up, I can use a bifilar, meaning 2 turns. But now I'm at 134. It doesn't fit. It says not fit layer. Okay, so how do I fix that? Well, I can make this smaller. Okay, this is telling me that I can use a 30. So I go to 30. I'm up to 86. That's pretty good. Okay, how about if I use 29? Will that work? Wow, I get even better, 96%. Okay, so I stop there. Now I come over here and I look at the power. Did it do me any good? Yeah, look at that. It went from 5.5 to 5.2. Okay, so let's see if we can still optimize this more. Here the 12 volts is only 44% filled. Okay, so now let's try a 2. I'm fine, everything looks good, but it's at 89%. If I use a trifilar means 3 wires. Again, look at that, it's 134. Okay, and this should actually say not filled. There you go. Okay, so then I look here. It says that I can do it with a 32. So I go to 32 and just back to 69. Okay, but let's say, can I go with a 30? Okay, getting there. 30. Can I go with a 29? 96. So I can use 29 with 3 wires and 96% filled. Here again, do the same thing. I go to 2. No, I'm 50%. Let's go 3. I'm 73%. Go 4. 98%. So I got 96, 96, 98, and this is close enough. Okay, well now let's look at the power. Okay, now I went from 5.5 watts of power dissipated to 4.7. Okay, so this is a much better design. So this would be the final design, and this would tell you that you can use 4 wires at gauge 20, 3 wires at gauge 29, 2 wires at gauge 29, and they would carry all the current, and it would be an optimal or a good, or at least a second pass design. All right, so anyway, I'm going to go ahead and stop here, and in the next video I'm going to see if we can simulate this, or we've actually simulated it. And what I want to do is, or one of the things that I want to point out here is that when you're doing multiple supplies, every supply or output has to have its own output inductor. So I'm going to go in the next one, show you how to calculate this. Actually, I've already shown this, but the new wrinkle is how to make these coupled inductors. Okay, so instead of having an individual inductor here, 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 we can wind all 3 inductors in the same core, and by doing that, by using one core, it saves you space. But there's another benefit of using the cross or the couple inductors. In that it gives you, or actually it improves cross regulation. Okay, and this is non-trivial. As a matter of fact, it's a little tricky, because if you don't use the right turns ratio, you can have circulating currents. which will cause ripple. Okay. Alrighty. So hopefully, I hope you found this video. I know it's a little long and it's a lot of material, but I hope you found it informative. And if you have any questions, feel free to email me here or on my home web address. Thank you for watching. Thank you.